Okay, can you see the entire screen now?
Yeah, it looks good. Yes.
Yeah, that's a beautiful southern Seyfert 1 galaxy with a barred spiral. Uh, so I don't have a lot of new things to say, but sometimes even just saying old things might be useful because my impression going to lots of meetings about AGN is a lot of people learn a lot of general things about AGN, maybe in graduate school. You hear these things a lot, which I'm not sure that they are actually true. And so maybe it's just that I'm a little bit more skeptical than other people. But in some cases, I was responsible for people believing these things in the first place. So I feel I have some obligation to warn you that not everything that you think that you might know about AGN is certainly established or not so certain. For example, we hear many, many times as soon as someone talks about the AGN, they assume that there is some kind of dust torus around it, and you've seen many drawings of these unrealistic things. And the second part of the assumption, which is even more subject to question, is the particular kind of torus is actually a big donut which wraps around the central engine in its equator, and that the only difference between, for example, a Seyfert 1 where you see broad lines or a Seyfert 2 where you do not see the broad lines, they are supposed to be intrinsically identical except for the viewing angle of this aligned torus, which must be very fat. So that is the thing I like about that model, although it is completely unphysical, but it does, because there's nothing which can keep dust up out of the plane. Just orbiting in some kind of cylinder is impossible. But at least this model does give very specific predictions, observational tests, and it really has failed most of the tests. So let's think a little bit for a minute. Well, what do we really know about the dust which is in an AGN? We could try to tell about it in this torus model from what is blocked, what is absorbed, what you don't see. Or we could, if we were lucky, maybe we could see some thermal dust emission, because wherever the dust is in the AGN, if it's close to the center, like the torus is supposed to be close to the center, it's closer than the narrow line region, for example, it should be pretty hot because of the energy it gets from the AGN. So the nice thing, of course, about the infrared is it's ideal for finding where the dust is. And so that we'll start with the question, can we should have a unique capability, for example, in NEP to discover red AGN. The hunt is on for the red AGN. Okay, whoops, did I just stop the sharing? Or can you still see my, okay, you can still see it, good. Okay, so this was done very effectively with WISE selection of quasars from an all-sky survey in Anson Lamb's thesis at UCLA. And this is a sort of a typical powerful quasar. You can already see some of the characteristics we're expecting for dust. But of course, it doesn't tell you if it's a torus. You see a sort of an unreddened quasar would look like this, with a very strong ultraviolet excess where most of the energy is. But these red quasars that other people, including Anson, have been able to find really are going down very rapidly in the blue there, and that looks like dust absorption. But at the same time, you can see, compared to a normal galaxy, a spiral galaxy might look like the green curve here, which has been fitted. There seems to be a lot of extra warm, or I would say hot dust emission present in the quasar. So maybe this is showing you both of the things that tells us the dust, the absorption caused by dust in the UV, and then the emission caused by the hot dust in the mid infrared. Really, it's almost in the near infrared where you notice this most. Anyway, the point about this is that these red quasars do not necessarily require, well, it doesn't tell you what it requires. I mean, he was able to get a pretty good fit here with extinctions of OEB minus V of 0.7. That's actually a lot of extinction, isn't it? If you think about how much extinction that corresponds to in the ultraviolet. And his model fits, of course, it's just empirical, find that most of the energy of the quasar, it dominates the total energy the AGN output does. But I wanted to point out, sorry, this is a busy slide. So that might be an example maybe of A, where you just have a reddening law There's a screen of dust in front of the AGN, and maybe we could correct for that. However, and sometimes that happens. However, when people talk about obscured or reddened AGN or dusty AGN, they are not necessarily thinking about that, something that we could work with difficulty. Sometimes they're talking about option C, which is some parts of the AGN are just completely blocked. It's opaque because we may have tens of magnitudes of visual extinction. The X-rays may be, the soft X-rays must be completely absorbed, even the hard X-rays, because it could become Compton thick, above a column density of 10 to the 23. So what are we going to do in that case? It's a different idea from idea A, and sometimes A and C are sort of confused in people's minds. Well, we have to realize the possibility that different parts of the AGN might be obscured by different amounts, so that we can't really use a simple dust reddening law. And the thing that's really dangerous to me is, what if the obscuration is not the same in all directions? What if it's not, for example, a spherical ball of dust? If it was a spherical ball of dust, then I would agree that we would just look in our line of sight, which would be random, typical, and then we would do energy conservation. We just say, well, the same amount of energy is being absorbed on all lines of sight, and then it must be re-emitted. The absorbed energy must come back out in the infrared. I think that's the basic idea of Sigali, and that would be good. What if the geometry of the dust absorption is very non-spherical? So you can sort of see this ambiguity in this graph right here. We have estimates of so-called obscured quasars, and you can see that the percentage of obscured quasars, according to this study, is a very strongly decreasing function of the luminosity of the quasar. So if you have low luminosity objects, they claim that they're almost entirely obscured. But what they really mean here is they mean that they are narrow line objects, or Seyfert-2s. If you really want maybe a red quasar, such as Wise has discovered, those are actually rare everywhere, but they become more common at high luminosities. At high luminosities, it's more broad line objects that are dusty. And another interesting clue to this is that even if you use the infrared to select the AGN, you cannot find half of them in the X-rays at all. So you've been thinking maybe about a torus, but in fact, I'm telling you that there are other possibilities besides this strange, physically strange picture. For example, some of this absorption, for example, in those red quasars, could be coming from much more larger distance. These could just be molecular clouds in the galaxy, which might happen to block our line of sight. I don't think that that's really ruled out. The strongest evidence for this picture here, the unification picture, the accreting torus model, the strongest evidence is the famous polarized broad lines, which says that the equatorial observer has only an indirect view from scattering of the broad line region in the center. But remember, most Seyfert-2 galaxies really have not been detected in polarized broad lines. So we really don't, and we don't know we don't know what it is that's blocking our view to the center. There are many possibilities as long as they're not perfectly spherical. For example, just to open your mind to this, it might be that we have a wind or a warped disk. That, I think, is probably more physically realistic. And it doesn't, for one thing, it's more dynamical. Actually, it can orbit around without violating the laws of gravitational physics. And it can make some very interesting obscuration patterns, which depend on where you are. So, for example, here is a disk. This is just a little toy model, which is so warped, it's warped by about 80 degrees, that the axis of the central engine is coming out over a larger disk of dust. Like that. You could even have a disk which is so warped that it warps over by more than 90 degrees, and the jet might go back into the disk. I'm just trying to show you, if I don't know if any of these is correct, but we really don't know at all if a donut is, although it's a simple idea, if it's true. So how are we going to make progress? I think what you have to do is you have to do a statistics of what is the dust covering fraction in a sample of AGN, and try to figure out what we would see if we could look from all different directions of the sky. Well, that's actually been done now. For example, these are all, this graph, and this graph are attempts to show the luminosity functions of narrow line Seyfert 2s and broad line Seyfert 1s. This is supposed to be an isotropic emission line, the forbidden lines from the narrow line region, oxygen 2 and oxygen 3. And this may be isotropic also. This has also been done for radio continuum. The point is that all of these luminosity functions look about the same for Seyfert 1s and 2s. Not much difference. Of course, the broad lines are much stronger at high luminosities in the Seyfert 1s. That's because they have broad lines. But if you look at these graphs here, I don't see much difference. So that would suggest, if you really believe in the simple unification picture, that half of the sky would be blocked by some kind of dust obscuration. Okay, so how can we use the infrared emission to find a complete census of these objects? I think that, as you all know, the most powerful way to do this is not to look in the optical so much, or the, say, at 1 micron here, because normal galaxies, which are shown by these solid lines here, look not so easy to distinguish from an AGN in the center of the galaxy. Where they open up their differences are in the short infrared wavelengths, where you can see suddenly, compared to the host galaxy, there's a high contrast. The AGN is maybe 5 times brighter. So I want to work out here to look for objects that have an excess around 2 or 3 microns. That's really where this excess peaks, 2, 3, or 4 microns. And so skip that. This was an attempt to do this. I mean, this is not deep learning or any kind of neural network at all. It's just looking at colors of AGN. Here are a bunch of AGN here. Here are a bunch of normal galaxies. And you see down here what is the discrimination or the success rate. And the 2 micron excess and then the 4 micron excess are the strongest measures we have that differentiate between just a normal spiral galaxy and an AGN here. These other colors, like what happens at 12 microns, are not actually very good. But even if you use this method, and even if you include, for example, X-ray detections, this is a graph of what we tried to do. The AGN we're trying to find are red. So here we put a cut. We want very hot dust to be present, but that doesn't necessarily give us all of the AGNs. Some of them don't have such a strong color signature. And in fact, even if we include the X-rays, we require that the X-rays must be detected, that might not work. We miss a lot of AGN that can be found in the infrared, but not found in the X-rays. So it's not trivial task to find them all. So just to make my third complaint here, the X-rays by themselves are not actually a solution to all of our problems, because, as you know, many Seyfert galaxies do not really show strong, even hard X-rays here. All of the diamonds here, this is from our local sample of Seyferts, the diamonds are X-ray AGN. But you see, as you get to high column densities here, they are really getting so weak in the X-rays that they don't stand out very much, and they become difficult to separate them from these little symbols, which are just normal spiral galaxies. So the problem is that unless once the X-rays start getting absorbed by these large column densities, you will have a really difficult time. Maybe, I don't know, even with E Rosita, we're going to have a hard time. And this graph is even missing a substantial number of Seyfert galaxies that could not be detected at all in the hard X-rays. Let's skip that one. So what is another way then where we're looking for a sign that there is a high energy spectrum of hard photons ionizing the gas that's coming from an active galactic nucleus? It's not just coming from H2 regions. Well, that is a good way to try to find them. But here, one of the things I'm very worried about is what how much of this galaxy, there's a big galaxy there, how much of the galaxy is being included in your spectroscopic measurement? Yes, if you just measure the center of the nucleus of this galaxy, you will see strong effects from the AGN. But as you go to higher redshifts, you don't have much spatial resolution. You're taking in much of the host galaxy disk. So we did an experiment here where we measured a BPT diagram. These are for, it's complicated, these are for Seyfert 2s up here and Seyfert 1s here. And what we did is we measured the nucleus. The nucleus, the center, is the red points. And then we measured the entire galaxy, what you would find if you measured it at a high redshift with a big slit, maybe Sloan or something like that. You notice that all of these galaxies move to some extent from the pure AGN region down to the star-forming region. The average is the green point. So a Seyfert galaxy, when you include a lot of the host galaxy, still looks like a Seyfert galaxy, but a lot less. It looks like a composite object, which leads to my next point. As you realize, every single Seyfert galaxy is a composite object. There's almost no wavelengths that you can look at where you're not getting some contribution from H2 regions in the disk of the galaxy and some other contribution from the AGN. And I'm glad that many people at the meeting here are well aware of that and keep that in their minds. I mean, okay, my final thing I just wanted to put up before we go is, in case you were thinking about trying to measure black hole masses by using the width of the broad lines, I think you should be very careful, even though I was largely responsible for people starting to do this, because it's very uncertain. In effect, you are really just measuring, when you try to measure the black hole mass, you're just taking the line width squared and you're multiplying it times the radius of the, v squared is equal to gm over r. So you're taking r times v squared. But how do you know what r, the size of the broadline region, is? It's usually just done by taking the square root of the luminosity, which I don't trust. Anyway, this was a claim that black holes at higher redshifts are bigger for a given size of host galaxy than today, but I'm afraid that I don't really trust any of this stuff. There's just so much scatter. Just to show you a recent attempt to clean this up, it didn't really get very clean. Here's our red galaxies. I mean, I could almost tell you in advance that most galaxies, you will measure the starlight. It has something like 150 kilometers a second of dispersion, and the broad lines will be about 3,000 kilometers a second wide. That's just what they all are. But you could be off by a factor of 10 in estimating what the black hole mass is. Yes, I mean, it's probably right to a factor of 10, but that might not be good enough. So just some warnings to be very careful if you want to know accurate black hole masses, just by using the width of the broad lines. They're always about the same. So I'm done. Hope that wasn't too depressing. Just wanted to give you, I tell this to everybody at meetings, when we're drinking a beer, after the talks, if we have a coffee or something, but I don't have a chance to do that right now. So if some of you have not already heard these complaints, now at least I had a chance to. Thank you.
Okay, thank you, Matt. Very nice talk. But we don't have enough time for Q&A.
That's right. It's okay.
So, and people ask questions on Slacks. So,
that's fine.
Thank you. So, shall we move on to the